Friends, Romans, countrymen, lend me your ears. I'd like to tell you about the rational roots theorem, the complex zeros theorem, Descartes' rule of signs, and the upper and lower bound theorem. These four tools are going to help us identify the zeros of polynomials. Let's get started. The rational roots theorem. This is easiest to explain by example, okay? Let's say I have a polynomial and its roots are -1/2 and positive how about 5/3. So this is going to be quadratic, I guess. These are the two roots, okay? So what are the factors? Roots and factors, two sides of the same coin. I can get the factor from the root. The numerator gets negated, so this is a +1 and this is a -5. And then the denominator is the coefficient on the x. So this is 2x + 1, and this is 3x - 5, yeah? Oh, hold on 1 second. Be right back. And here we go. So if I want to know what the polynomial is, all I got to do is FOIL. Hold on, I'm going to sneeze. Okay. Okay. 2x times 3x is 6x squared. Then 3x times 1 is inside. Outside is -10x, and last is -5. So this is 6x squared plus 13x - 5. And I don't really care about the 13x right now. What I care about is this 6 was 2x times 3x made 6x squared. And then 1 times -5 made -5. Why is that exciting? Because that means that this guy and this guy are both factors of this constant term. And it means that this guy and this guy are both factors of the leading term. They have to be based on the way we multiply factors to get a polynomial. So this wouldn't work if I had some crazy root like a complex number or a square root of 2 or some crap like that. It only works for fractions because fractions have these nice factors. But if your root is a fraction, and whole numbers count as fractions, right? Because 4 divided by 1 is 4. So 4 counts as a fraction. But if a root is a fraction, then you could think back to this example anytime you forget which one is which. It'll happen all the time. The numerator has to go into the constant term. The denominator has to go into the leading term. So I don't really know a better way to write that. Is a factor of the constant term, and the denominator is a factor of the leading term. This is the rational roots theorem. It tells you basically what I just wrote here. By the way, I love how much this looks like a veins and arteries diagram. That wasn't intentional. But all right, let me show you an example. I mean, this was an example, but this was a very small example, right? So the denominators 2 and 3 both go into 6. The numerators 1 and 5 both go into -5. It's a consequence of the way that polynomials are built out of their factors, because when you FOIL, all of these leading terms go into the leading term, and all of these constant terms go into the constant term. The leading terms were the denominators, and the constant terms were the numerators. So here's a big dang monster polynomial. Let's take 5x to the 4th minus 18x cubed plus, nope, not plus, minus 10x squared plus 50x plus 21. Check it. I need to check my own diagram. I always forget which one's the leader and which one's the constant. But if you just multiply a binomial, if you just multiply two linears into a quadratic, it'll come to you. Because these, the leaders are the denominator. Okay. So this 5 right here is your denominator, and its factors are 1 and 5. Those are the only numbers that could be a denominator. Your 21, it has factors of 1, 3, 7, and 21. Those are the only numbers that could be the numerator. So, possible rational roots. Oh, I should explain what the word rational means. It's not rational as in like clear-headed, it's rational as in ratio null. A ratio is another word for a fraction, right? Okay, so the possible rational roots. The numerator could be 1, 3, 7, or 21. The denominator could be 1 or 5. Oh, and we have no way to tell whether these things are positive or negative, so I'll slap a plus or minus sign out front like this. If I wanted to write out all of these roots, I could have 1, 3, 7, or 21 in the numerator. So any of these is positive, any of them is negative, any of them divided by 5, or negative any of them divided by 5. I know that's a lot. But there we go. So 1 or 3 or 7 or 21, and they could be alone. They could be divided by 1, like these, or divided by 5, like these. They could be positive, like rows 1 and 3, or negative, like rows 2 and 4. So what that means is, if this polynomial has any rational roots, and we're not guaranteed that it does, maybe all of its roots are complex numbers or horrible square root monsters, but if some of them are just plain old fractions, they have to come from this list. So like, I know right off the bat, I know 2 is not a root. I know 6 is not a root. I know 18 is not a root because they're not on this list. I know 1/2 is not a root. It's not on the list. So now there's only 16 possibilities, and if I were just going in blind, I would start with the small ones and just start doing synthetic division. And eventually I'd hit on one that works. It turns out that the polynomial's roots are 1 plus root 2, 1 minus root 2, 3, and negative 7/5. These guys are not rational. They've got square roots and crap in them. If there's square roots or imaginary numbers and you can't get rid of them, it's not rational. So since they're not rational, they're not on the list, of course. The list is only for rationals. But these guys right here, these are both fractions. I mean, the 3 is like a 3 divided by 1, but we don't write it that way. So it counts, it's on the list. They're rational, so they must be on the list. So if I got through the whole list and I didn't find any rationals, I'd know there were no rationals. So there you go. Oh, man. How long have I been lecturing? Everything 3.5 all the way up to here, these last 6 lectures, these are all me doing this on the same day. It's been June 17th this whole entire time. I mean, I guess it says so right here, don't it? Starting to wear down, but I really want to get this done today. So let me see where I'm going next. Let's say g of x is 2x cubed minus 3x squared plus 8x plus 7. I could ask something like, is 3 a root? And the answer is no, it's not a factor of 7. 3 over 1, 1 works. 1 goes into 2. So this is like 3 over 1. 1 goes into 2 just fine, but 3 does not go into 7. So, can't be a root. If 3 were a root, then x minus 3 would be a factor, and when I FOILed that x minus 3, the x would be part of the 2x cubed, and the minus 3 would be a part of 7, but minus 3 is not a part of 7. And so, I know that 3 is not a root. Make sense? It's not on the list. The list is going to be 1, 7, 1 half, 7 halves, and then negatives of all of those. Usually we just write the positive ones and slap a plus or minus in front like real lazy people. So then I could ask, is 7 a root? And it is on the list, so the answer is maybe. Rational roots theorem doesn't rule it out. We actually have to check. 7 goes 2, whoops. My coefficients are 2, -3, 8, and 7. Bring the 2 down. Multiply for 14, add for 11. Multiply for 77. I have a sinking feeling now that I'm going to get a big old number. Add for 85. 7 times 85 happens to be 595. Quick and dirty way to get that. 7 times 8 is 56, so that gives me a 560. 7 times 5 is 35. 560 plus 35 is 595. And 7 plus 595 is 602, so the answer is no. G of 7 is not 0, it's 602. It's a big honkin' number. So, and I could have also said, what is 2 times 7 cubed, so 2 of 343s, minus 3 49s, plus 8 7s plus 7s. But I think you'll agree that this is faster than saying 2 times 343 is 686, minus 3 times 49, so minus 147. My goodness, I don't know. I can't do that in my head. So I do this instead. I could do this in my head if you had a gun to it. Not evaluating. I guess I could probably evaluate in my head too, but I'd be real grumpy the whole time. So let's do another example. Now let's say f of x is, I don't know, what's this example even about? Oh, okay. We're gonna find all the roots of this polynomial, hey? 2x cubed plus x squared minus x plus 10. So the rational roots theorem gets you a list to start with, and wow, I lost my train of thought. It really is late. The rational roots theorem gets you a list of possible roots, and you use synthetic division to test them. I'll show you some theorems in a second that help you narrow the list down so you don't have to look at 16 goddamn things. So we'll narrow the roots down with some other theorems that we haven't seen yet. Those are the DROS and the ULT and the CZT. But until we get those, we're just going to try the entire rational roots list until we hit on something that works. So what's the list here? The leader is a 2, so we're going to divide by a 1 or a 2. The ender down here, the constant term is a 10, so our numerator is going to be 1, 2, 5, or 10. Have to list all the factors, yo. And there you go. So I have 1, 2, 5, or 10 divided by 1 or 2. There's not quite 16 things on the list. There's 1, 2, 5, 10, 1 half, 2 halves, 5 halves, and 10 halves, sure. But actually, 2 halves is already on the list. It's 1. And 10 halves is already on the list. It's 5. So there's these 6 things on the list. Any one of them could be positive or negative. So really, my list is 12 numbers long. So if I ask, is 4 a root? The answer is nope. It's not on the list. So I'll ask, is -2 a root? The answer is, well, it's on the list, so maybe. Not everything on the list is going to be a root, but I mean, it's on the list, so maybe. 4 is a rational number, and it's not on the list, so it can't be a root. If I say, is the square root of 12 a root? Well, the answer is, well, maybe. It's not on the list, so it's possible. But, I mean, like, square root of 12, it's not a rational number, so it doesn't need to be on the list to be possible. 4 is a rational number, so it needs to be on the list if it's going to be possible. Same way I can say 3 and 7 and 19 can't be roots. They're not on this list, even though they're good old fractions. So to find out if -2 is a root, I'm going to put it in a box and write down my coefficients, 2, 1, -1, and 10. And we synthetic divide, bring the 2 down. And now to go up a row, we multiply by c. So 2 times -2 is -4. To go down a row, we add. 1 plus -4 is -3. Multiply, +6. Add, +5. Oh, good news. Multiply, -10. Add, remainder of 0. So scratch that. The answer is actually yes, because the remainder is 0. That means it goes in evenly. So we've got a root. So I can say f of x is the same as x plus 2. That's the factor for a root of -2. Yeah, x plus 2, because a -2 would make that 0. And multiplied by, sorry, one moment. Multiplied by this here quotient. Technical difficulties. Quotient was, oh my gosh. Okay, I'm just going to live with it. 2x squared minus 3x plus 5, yeah? And a remainder of 0, so I don't got to write it. So I just factored a linear out of f of x. And now, do I keep going through this list? I don't have to. I've got a quadratic, and I know a faster way to bust that open. And that is, here x equals -2, but here x equals -b, +3, plus or minus root b squared, that's 9, minus 4ac, that's 20. That's not 20. 4ac is, shoot, my goodness, 40. B squared minus 4ac. Yeah, 40. All divided by 2a, so all divided by 4. I can't simplify that much. 9 minus 40 is -31, so I'm going to write 3 plus or minus root 31i, all divided by 4. And would you look at that? These two fellas, they are complex conjugates of each other. That will always happen. That's the conjugate complex zeros theorem. And that says that complex roots come in pairs, a plus bi and a minus bi. So for example, if I told you that 5 minus I was a root, you'd say, well then obviously 5 plus I is a root. They have to come in pairs. It's the only way. The only way to get around complex roots coming in pairs is to make some of your coefficients complex numbers. But we never do that in this class, so don't worry about it. So I found my 3 roots. So these guys are not rational numbers. They're ugly, awful, square root complex monster guys. So they don't have to be on the list to be included. But -2, it is a rational number, so it only gets to be a root because it's on this list. And try one more time here. Get this set up all nice. All right. Tell you what, that was a lot of technology for one video, so let's break this into chunks. I'll see you in a moment.